Okay, today we're going to spend a little bit of lecture time on a topic called function pointers. And I am going to post a lecture Thursday as well because we're a little bit behind where I want it to be. And remember, you are going to have your exam on Thursday. So rather than posting that lecture on Thursday, I'll probably post it next Tuesday. If you could watch that over Thanksgiving break, that would probably be useful. And then after Thanksgiving break, we're going to dig in and do a little bit of C++ to prime you for what you're going to do next semester in data structures class. So the stuff that you're learning in here, you're going to need to know, you're going to need to use it in that next class. So take it seriously. Also keep in mind for that final exam that if you do well on that final exam, then that can replace your midterm grade if you do better than you did on the midterm. So those of you who did poorly on the midterm, you have a chance to recover from this class with a very good grade, but you need to take it seriously and learn the stuff that we're doing here. All right, so today we're going to look at a topic called function pointers. And with function pointers, essentially, let's just dig into it and see about it. So first off, a little bit more with functions to kind of round out our understanding of functions. So functions are like the building block kind of core concept that's used throughout C language. Even the I've got to fix that. Even the place where the program starts is in a special function called the main function. Everything that you call in the standard library, printf, getS, fgetS, scanf, all of those things in the standard library, strcmp, strlen, string length, string compare, string copy, string concatenation, all of those are functions. It's all functions. So all code kind of lives in a function. And we've been using functions all semester, so let's take a little bit closer look at some of the things that we've seen. So first off, in C, all arguments are passed by values. So everything that gets passed to a function is passed by a value. In other words, there's no place where it kind of automatically passes a reference or an address for us. We have to explicitly do that. So in other words, if we want to pass a reference, then we have to explicitly put the ampersand in front of the thing or pass something that evaluates as an address, but we're passing the value of that address to that function. It's not, the compiler isn't automatically doing that for us. Other languages aren't like that. There are other languages where you pass some things and it's a reference, and some other things it's a value. And maybe you've seen that in something like Python, where if you pass an object to a function, that function can interact with that object instance through that reference and actually modify the object itself that was passed in. In C, we have to explicitly pass the value of the address, or pass something that is an address. It won't do that for us. So functions can also only return a single value when we use the return statement. So in other words, when we say return, you can't have a list of things that gets returned. Now, there are some ways around that, and that's not really any different than a language like Python. There's only one thing you're allowed to return, but it can have multiple items inside of that one thing. So let's take a look at that a little more closely. So the function return types can only return a single value using return. The return type can be any type except an array or a function. That's supposed to say or a function. And to return multiple values, it is possible. One of the ways you could do that is by passing pointers into the function as arguments. And then since that argument comes in as an address of the data item that was passed in, we can then have that function interact with and change that data item directly. So you could pass in a pointer to 3 different things in arguments and have the function update or change those 3 different things, which is effectively not really the same as using return to return 3 things, but it's a way to get 3 different pieces of data out of that function because we passed pointers to where we wanted it to update the data in memory. It then went to those places in memory and did that. So the other way we can pass multiple or return multiple things from a function is you can actually have a function that returns an entire structure. And remember, inside of a structure, you can have multiple data items. So for example, you could have a structure that's like a, for example, well, earlier we had like a bullet structure. And in that bullet structure, it might have an X coordinate, a y coordinate. It might have a velocity component, vectors, vx, vy. It might have a time that it's been alive or number of frames that it's gone through. So all of those things, we could have a function like create new bullet that returns a new one of those structures that has those things in it. So that's essentially returning multiple data items, but it's really only returning one structure. But one thing to note about returning structures is that can be inefficient because we're returning a lot of data. A more common practice you'll see in C is for us to allocate that some kind of structure outside of that, pass the address of it to a function, and then have that function modify the contents of that structure to set it up the way that we want it to. And that's less efficient because the only thing we're doing is passing an address and then accessing the data directly rather than having to return a whole lot of data that makes up some sort of thing like a structure. Now, return values that we say inside of a function where we return something, it has to match or be assignment compatible with a defined return type of a function. So every function in C has a defined return type. It might be void, saying it's not going to return anything, but it could also be an integer or a float or a structure or a pointer to some kind of type. But it has to, whatever we return has to either match exactly or be what's called assignment compatible with the return type. Let's look at an example of that. So here's an example. We have this function that has a return type of float f1, and then inside of the function, I made several different types in here. Notice if I return f, that's okay because f is a float, that matches the return type. If I say return I, that's an int, that doesn't match the return type, but it's assignment compatible with it, meaning as long as we could say float f equal I, and it could do an implicit cast, then that'll do that here when we return I. It'll implicit cast this as a float and then return it because those are assignment compatible. I can even return this single character, which would be, in this case, it has a 0 in it, but that's assignment compatible with a float. But I could not return a pointer as a float because those are not assignment compatible. I also, if I say just return without anything after it, that is actually undefined. That what gets returned could be garbage values, or it could be 0, or it could be on some compilers that would generate an error, but it's going to generate a warning either way. But note that if I say return that, some compilers will return nothing, but you'll get random garbage float value returned. Some of them it'll get a 0. Some of them will give you an error or warning when you compile. So main thing to note here, the return type after the return statement has to be assignment compatible with the function type, and that makes sense. Okay, a couple good programming practice tips here. Use a function prototype for any function you used in a source file somewhere. And again, the function prototype is a line that defines the return type of a function and the number of parameters or arguments passed to the function and the types of those parameters or arguments passed to a function. And so the rule is, before we use a function or call it, we should have a function prototype that tells us what those types and argument count are supposed to look like. Otherwise, the compiler has to guess, and you'll get some sort of implicit declaration warning. And the compiler, if it guesses wrong, you'll have your code won't work right. So good programming practice is always use a function prototype. Better programming practice is to put the function prototype in a header file that's the same as the name of the source file that the function lives in, .h. Put all of the prototypes in the header file, and then include that at the top of your source file for that, so you don't have to type them in twice. And then include the header file at the top of any other file that makes use of those functions that are in that, in this case, myfile.c. So that way, anytime you use that, you have access to the function prototypes, and the compiler can generate the right code. And notice that's something kind of like what we're doing. When you say pound include standard.io.h to use the printf function, you're telling it that getting the function prototype that tells what the printf function looks like at the top of that. One other thing is don't include things that aren't being used. So in other words, don't just include everything that you can think of. Only include things that you're actually using somewhere in your code. And the reason for that is that can slow down the build process. You're pulling things in that don't need to be pulled in. So only include things that are being used. Now, every function you call in your code somewhere should have a function prototype that's defined before the function is ever used in code. And whether that function prototype is explicitly typed in, or if that function prototype comes from an include file by pound including something, that is okay. But every function should have some sort of function prototype before the function is ever used in the code. And if you get an implicit declaration warning when you compile, you should fix that. You shouldn't just ignore that because what the compiler deduces and figures out now, there might be other code that gets put in your program that might change what assumptions it makes later. And just because it appears to work doesn't mean that it made the right guess when it implicitly tried to figure out what your function looked like. So always have a prototype for every function you call, and that prototype should be in the code before you actually use that function, which is why you tend to pound include things all the way at the top of the code. They don't have to be there, but that tends to be where it is. So we say, here are all the function prototypes for everything I'm going to use. We'll get those out of the way first at the top of the code, and then below that, declare any global variables we have or anything like that, any structures we're going to use in this source file. And then below that, you have, here's calling the functions and doing stuff. Okay, now, if a function is defined to return a value and we're purposefully ignoring that return value, in other words, let's say we have a function that returns int, but we don't really care about that int that it's returning. We care about what the function does. Maybe it prints out some stuff and it returns how many things it printed, and all we care about is that it printed the things, not how many things it printed. So we're going to ignore that. Well, in that case, it's usually good programming practice to cast the return of that function as void. And the reason for that isn't that it changes anything about the code that gets generated. It's a way to show other programmers that we purposefully ignored that return value. So here's an example down here. So here's an example where we have this function that's defined to return an integer, but it also does some stuff. I don't know, maybe it goes out and makes some files, or it initializes some things and it tells us how many things it initialized, whatever. But if we're going to ignore that when we call that function, rather than just calling f1, it's a good idea to cast the return value as void, because that shows another programmer who's looking at this code. They say, oh, they're calling f1, but f1 returns an integer. Why aren't they doing anything with that? They should be using that return value for something or checking it. This tells a future programmer or even our future self that when we look at this code in the future, okay, I meant to ignore that return value. And that's not necessary, but it's good programming practice. It's good. It communicates something to other developers. Now, you could also put a comment here that says, ignore the return value because we don't care. But a lot of times this casting as a void there without a comment has the same effect of informing future programmers, okay, purposefully ignoring that return value. All right, now we're on to function pointers, which was the topic of today's lecture. And before we dig into function pointers, I want to spend a little time remembering how arrays worked. So when you declare an array, like int AR10, that's declaring an array, a block of 10, a memory big enough to store 10 integers. And then down here, when we access that array or index that array, like here AR subscript 5, that's using the address of that array in memory and then moving 5 places past the beginning of that and then getting what's in memory at that place. So in other words, it's this thing pointed to by AR plus 5 is the same as what happens when we use AR subscript 5. And the reason that's important is because that also shows if I use AR by itself, the name of the array by itself, it evaluates as the address of the 0th position. It evaluates as the beginning of that block of memory, which is why AR plus 5 over here says start at that address, go 5 integer spaces past it, and then get what's actually at that location. So, important thing to note here, the name of the array by itself evaluates as the address of where that array lives in memory, where it starts in memory. So that means we can't change where the array is in memory. We can't increment it to move the array somewhere else. We can't assign it to some other value to move it somewhere else. So these things here are illegal, but we can certainly look at that address and then we can use it with, like, for example, here, the index operator, the square bracket operator. Or we could do point arithmetic on it directly and get the thing pointed to by that, but note that you cannot change it. Now that leads us to how functions work. So when we create a function, notice if I say void f1 in I, that's declaring a function called f1, has a name, and it has a type and a number of parameters that get passed to it, and it has a return type as well. Now, when I call the function f1 subscript 1, that's how I call and use that function. In other words, it's saying, go to this place in memory and pass this data to it. Similar, if you think about that, to what we're doing here. We're just using parentheses instead of square brackets. This is not passing 5 to that. It's indexing 5 away from that. This one is passing a 1 to this function and jumping to the place in memory where function 1 lives and executing the code that's there. Now, if I use the name of a function by itself, let me change these so they match the function up there. So if I use the name of that function by itself, that evaluates as the address of where in memory that function starts. And so that's the same as an array. AR used by itself evaluates as the address of where in memory that starts. So F1, when used by itself for this function, evaluates as the address of where in memory that function code lives, or where it starts. Now that also means I can't change it. I can't say F1 equals something. That's illegal because I can't move the function somewhere else in memory. It is where it is. Just like over here, I can't move an array somewhere else. I can't move a function somewhere else. And then the last thing here, this ptr equal f1, that's legal, that I can actually take that address and store it in a pointer variable as long as that pointer is an appropriate function pointer for this type of function. So that brings us to the concept of function pointers, which are really, a function pointer is just a variable that's holding the address, but the address of what it's holding it to, instead of an integer or a character pointer or a float pointer or whatever, it's a pointer to a function. So let's look at how to declare those. So declaring a function pointer variable, you basically do it like this: int, and then in parentheses, we put asterisk and then the name of the variable we want to create. And then after that, we put these empty parentheses. This says we're going to make a function pointer called fp1. It's going to hold the address of a function that returns an int type. Notice we still have our type, an int type associated with it. So this is an integer return function pointer. This is a void function pointer. This is an integer pointer function pointer. So we have to give them a return type. And then to assign them to the name or to the address, to take a function pointer and assign it to some actual function address, we do it a lot like we do with arrays. So we say fp1, like this function pointer 1, set it equal to the name of some function by itself. So notice that the sum underscore function, that would be the name of a function that we put by itself. We're not going to call the function. We're not going to index into it. We're not putting the ampersand on the front of it. We're actually just putting the name of the function by itself, because that evaluates as where in memory that function lives, the address of that function. Just like with arrays. The name of the array by itself evaluates as where that starts in memory. The name of a function by itself evaluates as the address of where that function starts in memory. Now, after we've saved that off inside of this function pointer, how do I call that function through the function pointer? Well, I can just call it like I would a regular function, or this does the same thing by putting the parentheses and the thing pointing to bar around it. That's considered preferred, and that's usually what I do. And you might ask, like, why? Why would I do that as a preferred method over this when they do the same thing, and this requires us to type 3 more characters? And the answer to that is actually pretty straightforward. The answer to that, like why do this instead of that, is because this, when I see this in the code, I can tell that that's a function pointer that I'm calling. This just looks like a function called fp1, and I might go hunting for where's that function fp1 implemented, and I might not find it because it's actually, I'm calling that function through a function pointer. This shows that it's a function pointer, and you can tell that just by looking at the code without any comments at all. If I see that, I know, okay, we're calling the function pointer fp1 there. But if I see this, it looks like, oh, they're calling function the actual function fp1 when there isn't an actual function fp1. It's just a function pointer that's holding the address of some other function, in this case, some function. Now, one thing that's probably important to note here is I see people when they're trying to, especially when they're first using function pointers, they'll try assigning the function pointer in weird ways like this. fp equals some function, they put the parentheses on there. That won't work because that's going to call that function some function, and whatever its return type is, whatever it returns, we're going to try to stick that into the function pointer. And unless that function returns a function pointer, that's not going to work. If that works like here, where it's just returning an int, you can't really stick the int that this created into a function pointer. Same thing like this. If I put the address of that, then we're going to call that function, and it's going to return to us some number, and we're going to try to get the address of that number and stick it in the function pointer. Not going to work. Also, if I do this, the address of the name of the function by itself, well, it's already the address, so we're trying to get the address of the address. That's not right either. So the way to do it, just like with arrays, use the name of the function by itself, because that evaluates as the address of where in memory that function starts, and then we can store that in a function pointer. Okay, so assigning function pointers, the return type of the function pointer has to match the return type of the function we're assigning. Mismatched return types are going to generate a compiler. In other words, if you have a function that returns a float and you try to stick the address of that into a function pointer that says it's for a structure return type, then it's not going to work. It's going to give you an error. And then calling that using the function pointer, we already talked about this, but I'm going to mention again, you can do this, name of the function pointer, parentheses after it, or you can do this, which is preferred. Or oddly, you can put as many asterisks as you want in front of that FP, because the thing pointed to by the function pointer evaluates as the same address that you had to begin with. So as many times as you say, give me the thing pointed to by 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 the function pointer, it's always going to point at that function. And if we get the thing pointed to by that function, it's going to be the function pointer and so forth. So you can really put as many as you want. But the thing that I would suggest doing is this second one here is probably the most used and the clearest to look at when you're looking at code to make it readable. Okay. Question that comes up is, why would we ever want to use function pointers? And it seems like a weird thing. Like, why do I want to have the address of this, where this code lives in memory? Why do I care about that? And there are a number of reasons. For example, it allows us to pass a function pointer to a function. In other words, I could pass the address of a function as a parameter to another function to have it do something with that function pointer. And a good way to think about this is a generic sort routine. You have a sort routine that you've created, let's say like a sort function that puts things in order. And sometimes you want it to put them in order ascending. Sometimes you want to put them in order descending. And the types of things you might want to put in order. Sometimes they might be floats. Sometimes they might be structures. Sometimes they might be structures of Z order points where you want it to sort them by their Z depth. Sometimes it might be structures that are student records that you want to sort alphabetically. Sometimes you might be student records and you want to sort them by the, the grade point average or the student ID number. And so how would you make a generic function that can do all of those different things? Well, you would need to pass in some sort of a pointer to a function that compares the things in some way. And so think of that generic sort routine where you pass in a function that does the comparison for grade point averages, and then you have a different function that does the comparison for student ID numbers, and a different one that does things alphabetically. And so you just call that generic sort routine, pass a pointer to your comparison function in, and it handles all the rest of the stuff for sorting it. Now, a second reason is to allow us to create user reassignable functions. And those are actually a pretty important reason. For example, auto-detecting hardware and then changing out how we do that. So for example, what function gets called to check if a key was pressed and do something with that keyboard information? Well, that could change depending on what kind of keyboard you have. It might be a wireless keyboard. It might be a keyboard on the laptop. It might be a USB keyboard that gets plugged in. And so you need to have your code swap out the get key thing depending on what keyboard it finds. And so to do that, we need some kind of pluggable architecture that, rather than having a bunch of if statements, it just says, hey, if I detect a USB keyboard, then make the get key function do this. And an interesting place where that is used specifically is an example that where I've used that quite a bit is in the products I make. This little motion sensing chip here, that little this little system on board here. Actually, not this one specifically, but other ones. But what they do is I have different configurations for those motion sensing modules that use different grades of gyroscope or accelerometers with different G ranges, or magnetometers or barometers. And so what I have is the code is written that it will auto detect what components it finds and then swap out the function points for those. So for example, if I detect the really high-end gyro for like a unit that is for aerospace, or a really high G accelerometer that's used for like crash test dummies, then the code will automatically say, I detected that. And then when you call the get acceleration function, it plugs in the right code and does the right kind of conversion to put that into G based on the raw values that it reads. And so that is a way where it's auto detecting that and then swapping the get accelerometer values. It swaps in and out the right function pointer to do it the right way, depending on what hardware it detected. Also, one other thing that you can think of is it allows us to store function pointers inside of a structure, which if you think about that, that's a lot like object-oriented programming. We can make a function pointer that lives inside of a structure, and that function pointer inside that structure can then access the function as if it were a method. So just like object-oriented programming, where you might have a bullet, and then inside of that structure you'd have like a move bullet function pointer, and then you can point that at some function that lives in memory somewhere that actually updates the position of the bullet, and then we can call that just like we would an object-oriented programming thing, where you say like bullet.moveBullet parentheses, and it would actually move the bullet around. Another thing is to make swappable functions inside of something like a structure inside of data, where you could have, like, for example, let's say we're using a structure for non-player characters, but some of them need to behave differently than others. Some of them are like knights and some of them are wizards, and so we need them to take different actions depending on what class they are. So we could do that by, when we create a knight, swap in the knight function pointer for the AI for them. If they're wizards, swap in replace that function pointer with the wizard action function pointer. And so that way we can make one single data structure that can handle a large class of different kinds of things in our code. Also, it allows us to create what are called callback functions, and if you think about event-driven programming, that makes sense that you could create code that does something like, hey, whenever this event happens, then take this action automatically. Well, how can that action get taken? Well, we can pass a function pointer into some part of the code that says, here's the function I want you to run whenever this action happens. So these are all really useful things and really powerful things to be able to do. And you're going to see some of these things done later on, but the function pointers are incredibly powerful, and they can provide a way to do things that's much more efficient than having to have a big if-else-if block with a whole bunch of different function calls, and they can end up being much more efficient and creating this generic code, code that auto-detects things, code that swaps in one behavior for another behavior, code that looks and works a lot like object-oriented programming. It's still written in C, so it's still very fast, and then also event-driven programming. Okay, one other thing is that since a function pointer is a type, that means I can make a function that actually returns a function pointer. And I actually do this again in my hardware devices, that there's a function that called detect gyro, for example, and what it does is it goes through all of the things, queries all the things, looks for whatever gyros are connected, and then it returns the function pointer to the one that it found. Well, how do you make a function that returns a function pointer? Well, here's the name of the function. There are the parameters. The return type, in this case, is an int, pointer, parentheses around that, close parentheses there. So it looks just like creating a function pointer, but it's wrapped around this function with the parameters inside it. And the thing that we're going to return is going to be the address of some function. You can also make a function pointer that accepts as a parameter the function pointer, a pointer to a function. And we do that like this. And then from inside that function, we can now call the function that was passed in. And again, a good example like that we mentioned was kind of generic, a generic sorting algorithm. It turns out that the standard library is qsort, which is their implementation of quicksort, provably the fastest sorting algorithm for comparison-based sorting that there is. There's a implementation of that built into the standard library, but it doesn't really know what you're sorting, but it's designed in such a way that you can use it on anything, and it uses that. We pass in a function pointer to the comparison function we want to use to compare the two items, which lets us set it to be ascending, descending, structures looking at this field, structures looking at that field. We can set up that function however we want and just pass the pointer to that into that qsort function along with the two pointers or the pointer to the block of data and how big the data is. Okay, so that's it for today. Work on your labs, either lab 6 or the final lab 7 is posted as well. And really lab 7, that final lab should not be overly difficult. Essentially what you're going to be doing is converting your Game of Life program into an SDL graphics program. So if you got the SDL lab working and you got the Game of Life lab working, it's just kind of sticking the two together and then adding a little bit of code to render those things to the cells to the screen. And so read through that lab, see if you can get started on that. It really shouldn't be too hard. The big challenge you're going to have is how do you draw a rectangle on the screen. It actually turns out we were already doing that in the sample code, but you're going to have to figure, we were drawing a rectangle over the entire surface. So what I would suggest is going to libsdl.org, look at the documentation, see if you can figure out how do you draw a rectangle at a specific spot on the window. And it turns out that you're going to create a rectangle structure. You're going to put in an X and a Y for the upper left corner. You're going to put in a width and a height. And then you're going to pass that structure to that draw or that rect SDL rectangle function that we were using before, and it'll draw that rectangle there, and you can still specify the color of that. So look at the code for that. What I would do if I were you is get the drawing rectangle code working first, and then try to integrate those. And the main difference you're going to have in this code and the previous code is the before you had that display board function where it was just drawing asterisks or dots and asterisks. You're going to want to replace that. The rest of the code, the num neighbors, the init board, the other things, that's all going to be pretty much the same. The only thing that's going to be significantly different is obviously the display board is going to have to do a bunch of SDL rectangles, but you're still going to go through a loop, every row, every column, and then look in that array. If you see a 0, you're going to draw it dead. If you see a 1, you're going to draw it alive. So that's really just changing the color out and then drawing a rectangle. Okay, so that's it for today. Everybody stay safe. Study up for the final exam. The paper part, again, is on Thursday. Make sure you're ready for that. There are a number of resources for you to work through to be prepared for that. There's a study guide that has some practice questions. There's a version of that has some answers in it as well. There's all the practice questions from the midterm face-to-face bonus we did, the in-class bonus we did. I would look at those to see if you can solve those. And then also go through that outline in the study guide and make sure you understand the stuff there. And if you have questions or some things are fuzzy, you can always go back and rewatch the lectures. And you can also always, there is an SI for this class now, so make sure you can contact them, talk to them. And there's also me, so don't be shy or afraid to contact me. And I can come in and help you if you're stuck on something. Okay, so that's it for now. Everybody stay safe, wear a mask, work on your labs, primarily study for that exam though. Obviously working on the labs will help emphasize that, but make sure you study, make sure you're prepared. And the paper part of the exam is coming up next class, so be ready for that. Nope, you don't have to do any programming on the a laptop or anything like that, so you don't need to bring that. It is open book, open notes, so if you have paper notes, bring them. If you want to print out all the slides, feel free to do that, but be ready to take that exam on Thursday. All right, that's it for now. I'll talk to you soon. Study hard.